is our first seminar for systems engineering and engineering management for the academic year, so thank you all for coming. We're really excited today to have Laura Hart with us. Laura is a systems engineer for the MITRE Corporation, and if you actually Google model-based systems engineering talks and presentations that she's given, actually will come up in your first hits. So we are really happy to have her here, and even more excited that she is going to be teaching a model-based systems engineering course for us starting in the winter term. So if anybody's interested, please feel free to reach out to us. So with that, I'm going to turn it over to Laura.
Hello. So how many people in here are systems engineers? And what other kind of engineers do we have in here?
Electrical.
Electrical?
Chemical.
I work in systems engineering.
Systems? Everybody gets the chemical? Okay. Great. So I'm going to talk about model-based systems engineering. And find the right button. Sorry. So I currently work with the MITRE company. Prior to that, I worked 15 years at Lockheed Martin. And I've been doing model-based systems engineering in its kind of similar state right in the way I'll be talking about it today since about 2005, using some of the same techniques. And prior to that, I used some form of model-based systems engineering, and it was usually out of need. It was because of needing to be able to communicate and distribute work and make sure that when it came back, it could be integrated together. So we'll talk a little bit about the difference between model-based engineering, which the electrical engineers in the room, can you imagine doing your engineering work right now without having some type of modeling tool? You know, if you gave you a piece of paper, would that be, yeah, it'd be kind of hard. Or mechanical engineers give you a draft table and a pencil and a compass. So what we'll be talking about is that you've been doing model-based engineering for a long time. Model-based systems engineering, we also need to be able to use tools to help capture the knowledge and be able to integrate across the different domains. And we'll talk about the difference between MBE and MBSE. We'll do a real quick overview of SysML, that's the systems modeling language, specifically designed for the systems engineer. And a little bit about a methodology. There's different methodologies, but we'll just kind of touch on the fact that you need a methodology to help you with systems engineering and managing the models. And we'll look at OOSIM. And if you're going to be doing modeling, you want to have a repository to store your information in so that you can, act on that information and use it for different purposes. So model-based systems engineering is still systems engineering. You still have the same processes, but you're going to be using models to capture that information, understand how all the information is related, and then be able to use it to address different stakeholders and answer different questions. And it's not so much about the picture, but you use diagrams to communicate, but what's really important is the data underlying those diagrams that are in a repository. So in the past, we've been doing systems engineering for quite a long time. In a document-centric environment, we would create specifications and interfaces and requirements and system designs, and then we would do various analysis and trades and make decisions. But it was all in different kinds of documents. So when there was a change, it was hard to understand what the impact across the system would be. The future of systems engineering is in a model-centric environment, and the enablers to allow us to actually move from a document-based to a model-based is, a language, in this case, the systems modeling language, to allow us to communicate in an unambiguous way, some methodology that would guide us through the process, as well as some type of repository or tool to manage all the information in. So these three things right here. Because in that document-centric environment of all the different specifications, requirements, design, it was hard sometimes to understand whether that document was complete, whether there was inconsistencies between information in the document itself, how they related to the design and the test information. And if there was a change, it was hard to understand what that impact was. And in the, not that many years ago, when you had a change to a system, you would have to fill out a change impact statement. And it was like, we want to make this change to the system. And there'd be places for you to say, well, what are the impacts to the other systems? What are the impacts to the documentation? Because that documentation would have to go off, be changed as well. And a lot of this was just creating the change package itself was labor intensive. Those documents would be modified and someone would be given paper changes. Here's 12 pages, and they would go into the library and open up the books, take out the drawings, put the new ones in, and kind of labor intensive. In a model-based environment, the system itself is the record of truth. If you want to generate documents, you generate the documents from the model. It also allows you to kind of monitor your system and understand, are you complete? Is there inconsistencies? If I have different components, you can kind of query across the model and understand whether there's inconsistencies in the interfaces. So the enablers for model-based, some of the things that we would be learning in the class is the language that we would be using to communicate and capture our systems engineering content, some method to guide us through the process, and in the class we would have to use a tool. In the class I will be teaching, it will be MagicDraw. It's No Magic's MagicDraw, and that would be the tool we'd be using. And we would be, let's see. So, what is a model? It's a simplified version or concept. It could be, and what it would be, what is important for us to, when we're creating our model, is to understand, like, why are we creating it? So, you don't just sit down to model. You have a purpose in mind. Your models will vary depending on what you're addressing. But it's really a way to facilitate understanding or help make decisions or to explain or control or predict different events. And so when we start doing model-based systems engineering, the first thing we have to ask is, why are we doing it? What's the scope? Is our context an enterprise? Is it trying to understand what Lockheed Martin wants to, what capabilities a particular division has strengths in to support, determining what programs they want to go after, understanding that if they want to get these particular programs, they need to build up these capabilities, or is it to go build an F-35, jet? And again, that context would be very different depending on what your objectives and goals are. But those are the kind of things that we'll think about before we start modeling is, what is our context? What are our challenges? How is this going to be used in the end? Who's using it? What do they need? How would it be used throughout its life cycle? This model is not something that you create up front, hand off to someone, and then forget about. This is something that is going to represent the technical baseline, or what the system is, if it's a system, over its full life cycle. So, talked about what a model is, model-based engineering. Well, that's doing your engineering work using models. We've been doing that for years. We've been doing that for 20 plus years with 3D CAD models and electrical models. What's different about MBE today in the last several years is that we're looking at how those individual engineering domains are linked together. So it's not just the mechanical model separate. It is integrated with that systems engineering model, so that if something changes in one area, we can understand how it might impact another area. So for example, in the systems engineering overall view, you might say that there's a certain power, weight, and size constraint, and you would allocate, the systems engineer would be looking at that higher level view and allocate different power constraints to lower level components, as well as size and weight, and to make sure that everything will fit in the nose of that helicopter. Now, everything's fine down here in the 3D model as long as they're within their constraints. But as soon as one of them gets out of its constraints, if your whole thing is integrated, your various system models are integrated, there will be a notification at the higher level, and the systems engineer can say, well, we're just going to move these weight balances around. This one's, we're under over here, we're over here. Or they could say, this, not all these components will not fit in this nose, and therefore, we need to do some type of redesign because this will not fulfill the end goal. So that was a long explanation, but we've been doing model-based engineering for years, and what the shift is to have an integrated set of models across the various engineering domains. And the model-based systems engineering discipline is what is going to allow the integration across those other domains. So MBSE is basically model-based engineering for systems engineers. So it's those aspects of MBE specifically for SE. So the integration across engineering domains, it's broad. It starts from concept, system development, through production and operation and support. It also is at different levels of abstraction. You may start looking at the operational system to try to understand what system needs to be built. What system of systems need to come together to fulfill these operational goals, or it could be applied down at the lower component level. So, MBSE, it depends on what your scope is, can be at these various levels of abstraction. So some of the benefits is using. So I didn't really talk about the benefits of systems engineering. That's another topic. But model-based systems engineering is improved communication with our stakeholders, and our stakeholders are both internal and external stakeholders. Being able to manage complexity, being able to manage the system complexity, all the information's in the repository, and you pull out what you need to address a particular concern. So let's say that you wanted to create a separate verification plan for everything that was safety critical. You could basically query the model, and within these tools, they make it really easy to create a table of something that is a 5-minute task. Give me everything that's been tagged as safety critical, and create a table, and it's within the model. At that point, you can then start working off, creating a test plan for it and managing its life cycle at that point. Improve the quality, because no longer are things presented in Word or PowerPoint. When you try to the model itself can tell you when there's inconsistencies. It's hard to see that on paper. And reuse. What we've also seen is a big increase in being able to reuse different aspects of of a system. So for example, if you're a satellite company and you're building various satellites, at some point you will start reusing these different components within your satellites. It might be that for a particular satellite profile, you can say, we're going to reuse these 3 things, but we have to build one more custom thing to fulfill this mission. So companies that have been, come on in, and there's food in there. So as the organizations that are using ModelBased start maturing, they're also seeing a lot of reuse and starting to build libraries of components or even sets of requirements. So like different requirements can also be reused. And because there is more precision in the specification, and you can measure whether something's complete and consistent, and it allows us to reduce risk, because we can see inconsistencies early on in the life cycle. There is something that has been a term that's been used in the last couple of years, and it's really a government term. It's owning the technical baseline. And what that means is that the government wants to have more insight into their systems that are being built. These are large, long-lived systems, 20, 30-year-old systems, expected life cycles. And they want to be able to, over time, make informed decisions. And so part of enabling them to own the technical baseline, they are starting to turn to model-based systems engineering as well, so that there's a permanent record of authority that when they want to do a big mod upgrade to a ship or a aircraft or a constellation, that they have the technical information to make informed decisions. There are cases where there are radars that are 20 years old, and they can build them. They can build them reliably, but they can't go back and change them because there are decisions that were made that they no longer feel confident that they remember why those decisions were made. So it would be, so in this case, they would probably go back and redesign this system. If they had captured that tacit knowledge and some type of model and understood, well, when we made that decision, we did it for a reason, that's something that they're looking at going forward now. It's not just this is the system design, but why did we pick this over this? Why did we do this over this? And that's important information to capture as well. So how does it work? How does model-based systems engineering work? And how does the system model use to be that integrating construct? Well, we're developing a set of interconnected models using a standard language and visualization, and having a shared repository that this information is stored in. There's different stakeholders that care about different things, but there's one authoritative source of truth. So what that ends up looking like is, the system architecture model gives you that overall how everything fits together, high-level architecture and design, understanding what analysis needs to be done, what tests have to be, how things are going to be tested eventually. But the individual domains will use their own specialized tools. So you're not going to ask a mechanical engineer or electrical engineer to use SysML, but they would be getting their design constraints and requirements from the system architecture model. And there would be some type of linkage between them that would allow someone looking at the overall system to know when something down here happens that could potentially impact at a higher level. So there's two kinds of models that are really important to kind of understand the difference. One is that system architecture model, which is kind of descriptive in nature. It emphasizes how all the pieces fit together in a consistent whole. It's the repository that shows all the interrelationships between everything, and it's used to capture, the functions or behavior of the system, the structure or components that are going to be performing those different behaviors, the interfaces, the information being exchanged. It's basically the descriptive piece of the system, and it also provides the vehicle or construct to do analysis within. And then you have another kind of model that's just as critical and works along with that descriptive model, and that's the analytical models. Those analytical models are usually emphasizing something very specific, like some characteristic such as performance, or they're usually mathematically based or some type of simulation, and they're really used to reduce risk through analysis or validating a particular design. So in this case, the example is maybe it's an optimization of a measure of effectiveness or a key performance parameter of the system, or some type of timing or survivability or reliability. Or what's really important is understanding the total cost of ownership of that particular system throughout its whole life cycle. So they're a different kind of model, but they're closely related to that descriptive model. And these analytical models inform what will actually go into the descriptive model. And the descriptive model will provide the context for the analytical models. So let's say that you had two different kinds of optimization. You're building an underwater, little a submarine, a small unmanned submarine, and you have you're competing with how long it has to be able to its power, how long it can function autonomously, how far it can go, and you may have to do some trades on the power supply, the batteries. Well, as you give it more time or life, you're also increasing the size of your battery, which is giving you more weight, and then how does that impact your... So all these different competing properties, you can't just optimize power, you have to optimize the weight and size for that, to get the objective that you want. So those are the kinds of things that context model would allow you to do. If there's a difference, you think about the difference between how you would do things with disjointed documents versus a model. The information in a document-based is mostly text, different documents. Diagrams are ad hoc. A diagram over here, if you change it, doesn't change it over here. In a model, you define things once and you use them many times. So I can define how something simple, an Outlook server. I can define all the properties of an Outlook server. Think of it as almost like a catalog number. Here's an Outlook server, and I can use it in many different places, but it's only defined once. For documents, again, I'm sorry, I hit the wrong button. For information views, you communicate what's in your design using documents. In a model, you create different viewpoints that pulls out that same information but just visualizes it in a different way. Measuring impact, again, if you're in a document, you have to look at different documents and try to make that mental connection. Are these consistent? Whereas in a model, you can query the model and it's basically that's what it's made for. It's a natural part of the process. And measuring integrity and completeness, again, it's hard to kind of identify inconsistencies when you're just reading a document. It's pretty easy to do inside of a model. So if I'm looking on page 12 and there's a diagram there and there's an interface between two things, and I look on page 36, I might not recognize that there's an inconsistency there, but a model you can. So some of the guiding principles are that people, processes, and tools. We need an effective way of sharing engineering data. The data we need to identify what data is common and shareable. The data must be organized well. And the data must be accessible by authorized users, and consistent and authoritative, and everything must be configuration managed. So some of the challenges with moving from document-centric systems engineering to model-based systems engineering is managing the model, making it easy for people to find what they're looking for, and also protecting the information and making sure that that you can only access what you're allowed to access, either in being able to read the data or even access the data. And in a very large model, need to know is also part of it, and being able to protect proprietary information. So there's a lot more to, because all the data is there. And if it's multiple companies working together, they may not want to share across these, the various companies. They may want to share what their external interfaces are and what, Lockheed needs to know this, Raytheon needs to know this, Boeing needs to know this, but they don't want each other looking inside and seeing their secret sauce, right? So these are some of the challenges we have with having these big integrated models is data rights and data protection. So good model organization is a key to doing that. So I'm going to talk a little bit now just about the language that supports systems engineering. It's SysML. It's a general purpose graphical modeling language. It allows you to represent structural things, compositions, behavior. Has anybody used SysML? Has anybody used a flow chart? Okay, so there's a diagram called activity diagram, and it looks a little bit like a flow chart, but it's more than that. Yes?
So you can run your queries from SysML?
Yeah, the tools allow you to query, and then like the activity diagrams. That's what looks a little bit like a flow chart. Will allow you to specify, like describe some type of behavior, and those behaviors can be, depending on what level of abstraction you're working, those behaviors could be something like, I want to do a battle damage assessment. There's a diagram called activity diagram, and it looks a little bit like a flow. So it could be very high level abstract level, like I need to do a battle damage assessment. What do I need to do? Do a flyover, do a drop, do a, go back and do an assessment. What do I do afterwards? Or that activity diagram could capture something like an algorithm for optimizing something. So the language is very general, and it can be used at different levels of abstraction, is the point here. It also allows you to capture requirements as first-class elements and then show relationships between those requirements. So within your model, you bring in your requirements, and then as you are addressing maybe a functional requirement, something that the system has to do, I might show a satisfaction relationship to some activity diagram that says, this is how I intend to do it. And at any point, because that formal relationship's there, I can create a table and say, show me all my requirements, which ones have I addressed? And then the same thing with the verification. So these are just part of, you need to do this in systems engineering. The models allow you to manage the work and understand when you're done. And then later on, when there is an intentional change to an existing system, you can say, well, if I change this, what potential areas might be impacted, and that's a big part of, or one of the benefits, is understanding change impact later on in an existing system. So SysML provides a means to capture the system modeling information as part of a repository. It supports different methodologies. There's different methodologies out there. There's traditional functional analysis, object-oriented techniques. There's different kinds of diagrams that capture those different aspects of your system: behavior, requirements, and structure. And this would be something that we would go into more detail in the class to discuss when you would use which diagrams to capture which within different systems engineering processes. So things that would, well, I'll show it in a second. So you're going to capture structural things in something called a block definition diagram. It's kind of used for defining all the things. Think of it as your bill of material. These are the things that we need. And an IBD, or internal block definition diagram, says in here how I'm going to use those things in a particular context for a particular reason, as well as what information has to be exchanged. You can then start formalizing what the interfaces look like. And of course, you can't see all that here in a model. You would click on that and you would actually see how that interface is defined and what information is allowable. There's different ways to capture, this is I'm talking about the language right now. There's different ways to capture behavior in SysML. This is a sequence diagram, and it's showing, and again, this is what we would be covering. It's showing two different components, a traction detector and a brake modulator, and understanding how they're sending signals back and forth to each other to support, some behavior. You can also, SysML also has the construct of a state machine, and there's different systems and different things. One mechanism is better than the other. Think about trying to describe how you would use your cell phone in every particular situation using a sequence diagram. It'd be, you wouldn't. It would take, because you can't predict, if I'm going to be playing Candy Crush while the phone rings, or am I going to be playing solitaire when the phone rings. You'd have to have all those different permutations. But you could see how a state machine would be very easy to capture the behavior of my phone. If I'm in the phone, in the state of playing a game and the phone rings, versus I'm on a phone call and the phone rings, those are two different states, and that's something I could probably capture in the something with the state machine. And again, and then this is the activity diagram. This is the thing that kind of looks like a flow chart. But these are this different kinds of construct the language allows you to use. You need to you have to figure out which one's best for the problem that you're addressing. Additionally, SysML has requirements diagrams, so you can understand how requirements relate to each other, how requirements relate to other elements within your model, as well as something called parametrics, where you're understanding the different constraints that the system may have and how they relate to each other. So in this case, I have a parametric diagram that talks about, how I would be evaluating a straight line vehicle dynamics, and what I would need, the equations I would need: a brake force equation, acceleration equation, velocity equation, and distance equation, and how the different parameters are feeding each other. And what's missing are the properties from the system itself. And this is how you would construct one of these to understand how the current configuration of the system might be, how it would might be optimized for straight line for this particular test case. So here's how these different constructs relate to each other. So the modeling tools allow you to capture these different aspects of a system, and then how they're related to each other. So in this case, you have some structure, and I'm not sure if I use my mouse for this. You have the structure, and over here you have the behavior, and you can see that there is a relationship between the structure and what it has to perform. And in this case, you see the structure, and if you want to see what behaviors it's going to perform, these are just whether you turn these visualizations off or on. So everything's the behavior, the structure, the constraints, and the requirements are all tightly related in the model. That's what I'm trying to say here. And so in this case, you're seeing that a requirement in the bottom left over here is satisfying some, is being satisfied by some structural aspect in the IBD, the traction detector, and in the behavior section over here, you're seeing that these behaviors or activities like detect loss of traction are being performed by these structural entities. Okay? And what this is also trying to show is that all these different aspects that you're capturing in your system model are related and connected to each other. So in this case, one of the value properties or attributes of this brake modulator feeds into, called duty cycles, feeds into this analysis to then calculate, this straight line vehicle dynamics, as well as the position of the vehicle. And then this is used to verify some requirement for a stopping distance of a certain, from 60 miles an hour within 150 feet on a clear, dry surface. So, and a lot of times you're trying to optimize different, multiple properties, and there are some sophisticated tools that allow you to integrate all these various analysis tools together. This is an example. We probably won't be doing that. And the fact that you need some type of methodology, OOSIM is just an example of one, and it'll kind of lead you through. You need to set up a project, how you're going to organize your model based on your organization and access rights. Then when you're analyzing the needs and engaging your stakeholders, how would you capture those concepts and communicate that with your stakeholders? Then defining the system requirements based on the stakeholder needs. Then defining some functional architecture, what it has to do, or logical architecture. A lot of times programs will leave this out. All of this needs to be tailored for individual programs. And then to synthesize some allocated architecture that you're actually specifying. And all along, you're also looking at capturing domain assumptions, common vocabularies, justifications of why you're making certain design decisions. And throughout the whole process, you're optimizing, making trades, and you're capturing all that knowledge of, like, when you make a decision, why you picked a certain outcome, as well as maybe why you didn't pick the other outcomes. So that 10 years down the line on this system that's going to live for 50 years, someone doesn't come in and say, oh, why didn't we do this? And then they make the change, and then they realize, oh, that's why they didn't do that. Always looking for opportunity for reuse and COTS and GOTS, government off-the-shelf and commercial off-the-shelf elements. And of course, always having traceability to your requirements and understanding how you're going to verify and validate that system so that you can actually get paid at the end. So those are things that we would be covering, as well as some methodology. And then you have to have a tool. The tool that we would be using would be MagicDraw. It's a UML, SysML compliant tool, and we would be using SysML. this is kind of what it looks like. Look over here on this side. On the left-hand side is called the Containment Window. That is actually the repository. It represents the elements within the repository. The right-hand side is the pictures. So I could delete all of my visual diagrams and I would still have the repository. And wrap it up here so y'all can ask questions. This is just an example of a model organization. In this case, it's a CubeSat reference model. And so we have other universities that have been using this CubeSat reference model as a starting place for them to learn model-based systems engineering and also build a CubeSat as one of their projects. And you can see how it allows you to create that organize and allocate different functionality to different subsystems. And in summary, this integrated model is supposed to be the source of truth. It helps bring different stakeholders together, and hopefully it captures knowledge about the system that's long-lived, that can live throughout the entire life cycle, and should improve quality and make our complex systems more affordable and to be able to maintain them over time, because a lot of our large systems, they've gotten away with just build a new one. It's like update your old one or use an existing system in the context of another system to get more capability. And so I hope that you consider signing up for Model-Based Systems Engineering. And then one real quick commercial. There is a new Drexel and Cozy chapter, the International Council of Systems Engineering, and your president is back here. Can you introduce yourself real quick?
Hey guys, I'm Davin Ross. I'm the president of Drexel's chapter of INCOSY, which is our systems engineering organization here. Just a quick plug for us. We're new to campus. We're looking at what we're going to do in the next year or two. We're looking at site visits and networking events. We have a lot of interaction with the Delaware Valley chapter. And we have a couple events coming out. So if you're interested in us, feel free to come and talk to me. Also look us up on Dragon Link. We're called INCOSY on there. That's all.
And that's INCOSE. So any questions? Yes?
I was wondering, have you personally ever been involved in an effort to stand up or convert from a document-centric to a model-based systems effort? Have you ever been involved in standing it up or converting it?
Yes.
What was that like? Because looking at it, it's just thinking about all the systems, the inventory, the cost flow, even putting a FAMICA in there is an incredible amount of work. So what was it? How do you go about even starting a process like that? What was the extent of the project involved?
So the last thing you said was how do you do a FAMICA, or how do you do risk, or how do you do cost, or how do you do one that we're looking at right now is how do we certify a brand new nuclear system? We've upgraded nuclear systems for years. What about a new one? What we ended up doing is building method libraries that says, okay, if we want to do cost, or we want to do risk, we want to do FAMICAs, this is how we do it. We want these properties, and we want these visualizations, and we modularize them, and we bring them into the model, and we reuse them. So we start building a library of things that we want to do. If we want to roll up weight and cost and risk, or not weight, cost, and power, then we created a method saying these are the properties we need, here's how we're going to do it, and we start building these libraries. Because it is hard to do everything at once.
I was going to say, how long did that take to implement from the beginning, from conception to completion?
So it would be a lot less now than it was 10 years ago. So what I initially started doing was how do you roll this out at Lockheed on large programs, and usually a lot of the textbooks talk about how do you do this from greenfield, from scratch on a brand new system, and here's a little example, right? The reality is that it's usually the people that see how it will benefit them are very large programs, and they already exist, and they're about to do a major upgrade to them. So there's a little different approach there. Let me answer your question. It's not just about the techniques, it's also about the processes, the existing processes, the people, and getting them to understand what the benefit is, and then training them to a level. And then piloting. You typically want to pilot something like this. Get them understanding what the process is and the value, and then start deploying it across the organization. And that was kind of the approach that we've had and have used. The other thing is it depends on if they're trying to institutionalize it at the enterprise, like this organization wants to do this, or if it's a particular program and they want to do it. And so it's kind of like, it depends. So one of the things I did when I was at Lockheed is, yes, we wanted to do it at the enterprise, but we addressed it at the program levels. And so the program wanted to go model-based, basically would interview them, figure out what their current skill rate was, then identify what tools they needed to support, because it's not just Cameo modeling tool, it's what requirements tools are they going to use? What's their configuration management? What organization is going to be working together, because that will affect how you're going to kind of organize your models so that you can protect the proprietary information if there's multiple contractors working. So it really depended on that. Then we would do just-in-time training. And then this is the part that we learned the hard way, is that you don't just do all that training, give them the tools, and then walk away. You need to have that ongoing mentoring, like making sure they're still on track, and see if there's, what kind of problems are you running into. So that ongoing mentoring for a while. And also having somebody that's identified as the one that's going to be your replacement when you leave. So mentoring them, training the trainer. So, but yes, it's you don't try to do everything.
Right.
And in one case, there was a program that says, we want to use model-based systems engineering, we want to use DORS for requirements, in this case, Rhapsody for our system model, and oh, by the way, we want to create DODAF views, which is Department of Defense Architectural Framework, another level of specification. And we're going to integrate with something called Phoenix Integration Model Center so that we can then use Satellite Toolkit to do our analysis. And there was like, okay, do you know this? No. Do you know this? No. Do you know this? No. Do you know that? Oh, a little bit. Okay, well, you need training here, 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 here. Why are you doing this? Well, we're not sure. Well, you need to know that. So anyway, it's there is a little, there's an investment that they have to make, and you don't just do it because everybody else is doing it. You're usually doing it for a reason. Did I answer your question?
Yeah.
Okay.
I have another specific question, but you go ahead. You have a question.
Yeah. So a lot of engineering systems, in my experience, end up outliving their lifespan or being applied to things like beyond their original scope. But the systems end up ultimately being too effective to the upstream customer's eyes to be replaced or to take some serious revamping. What are some criteria that you look at when you make the decision of fixing or improving a system that's already in place versus creating a new system?
Well, sometimes there's not a choice. It's like we need to improve this system, but we've lost that. Everyone that was on the design team have retired because it was a long-lived system, but it was really important. That's something that we're trying to address by when you use model-based today, you should be thinking about, if I'm using this 10 years from now, I need to know why we made certain design decisions. And you're exactly right, a lot of the systems are being repurposed within a larger system, and maybe not being used for its initial intent. And when I said something about owning a technical baseline, it was really to address the question, or what is happening where they don't want to build a new system. They want to be able to go back and understand, how do I modify this system or improve it. So this repository becomes both a learning and teaching tool when you have a new person come in. There's that tacit knowledge that's been captured, that organization where they can see, this is where I'm responsible, but I understand where I fit in the big picture, and I understand why certain decisions were made. So I think this is what we're trying to address, is that sometimes they didn't have that insight and realize that system was going to stay in the air 5 years longer than expected, or how valuable it would be. And you had another question?
This is more like a very specific question about the language itself. Like 2 questions. Like, one, do you know what companies like use SysML today? And then is there a function there, if I were to feed it like multiple Excel files or something, could it then do a function on the data that I feed it and put it into a different format for it? Like,
yeah, when you're starting with a new system, you might start with the modeling tool and create everything individually. But when you're starting with an existing system, you would probably take your Excel file.
I assume I can feed it information and it'll do something different. I've never used this language. I'm not familiar at all with it.
So it's not like MATLAB. It's not that kind of computational language. But
it's like an object-oriented more, right? Sorry,
yeah.
I didn't interrupt.
No. So if you had an existing system of like a list of components and attributes of those components and some definition of their interfaces, and it's all in Excel spreadsheet like a bill of material, you could import that into one of these tools and represent it as SysML blocks.
Okay.
And if they had relationships already created between them, you would see that in the model as well. So yes, we want, most of the time, we want to be able to import a bunch of data into these models to start with. We don't want to start
We have a question online. Is there a place in the model to put lessons learned and or why decisions were made?
Yes, absolutely. In fact, it is one of the benefits of doing this is to capture the rationales for why you made a decision. And there's sometimes I'll create you can extend the language too. And so when I have a new group, I would extend the language and create, instead of just having a problem or rationale, I might say a modeling question or a technical question, so that when we meet, I look at the table that's generated automatically and say, here's all the modeling questions. These are the questions that the newer group have about how to represent things. And then here are the technical questions, design questions that are about the system itself. Separate those two things. But the answer to the online person's question is absolutely yes. That's part of the strength, is understanding that why you made certain decisions when you did a trade. And in fact, it's part of that whole integrated system environment and set of models, including your system architecture model, is capturing the outputs of those trades, including the ones that you didn't select. Anybody else?
I just want to make one other comment. Laura is also the Delaware Valley chapter and COSI president. Like Davin said, we're linked with that. I'm the faculty advisor of our student chapter here, as well as with a board member of the Delaware Valley chapter. If you're interested in the COSI chapter that you have here, you can either go through Dragon Link, like Davin said, or I have business cards. My name is Rick Rangerino. You can just reach out to me and I'll put you in touch with Davin. But we had a lot of interesting things planned for the year, and we often have topics like this where we have expertise. I'm talking about subject matter experts talking about things like this. Any question?
We have another question online.
Okay.
How important and how often in practice do you need to actually be able to simulate in MagicDraw versus capturing in
So it depends on what you're simulating, but if you're looking at, the answer is yes, you can do simulation and execution of behavior in MagicDraw. And for example, if I want to look at functionally how the system, what the logic is to accomplish something, I may execute that and make sure that the interfaces are consistent and that the logic closes. If I want to do, and I can also execute these parametric constraints. If I want to do some type of sensitivity analysis, you might could do it in the Cameo or MagicDraw, but typically I would have a dedicated simulation model that might be integrated to like a, to actually execute like a discrete event simulation.
So basically, it's more used for documentation versus simulation. Oh, by
Simulating behavior.
you meant simulating behavior.
Okay, for simulating behavior, yes, you use Cameo. What do they call it today? I think it says Cameo Simulation Kit. Simulation Toolkit. It's STK. I don't use that because I also use something called Satellite Toolkit, which is STK. So there is a Cameo or MagicDraw simulation toolkit that you can execute, and yes, we use that, including state machines, activity diagrams, sequence diagrams, and parametric diagrams. You can execute all those. Yes.
The tools seem to be getting better and better for model-based simulation, but how good are they really with respect to integration? Like if you make a change in one document, does it filter through all the other documentation?
When you say document,
Well, if you make a change in one model, does it filter through to the other models?
so when you say other model, are you talking about something other than a MagicDraw model in this case, right?
Yeah, like let's say you mentioned that
Like
if you're an electrical engineer, you're interested in the documents that pertain to the electrical part of the system. So if you make a change, will it filter through to that documentation? I know that that's still been a...
No, yeah, you can do it, and I have done it. Not everyone does that, but that is kind of the overall goal is to understand how those are related. And there's different ways of doing that. One is through something called linked data, OSLC linked data, and it's done for sure with requirements. So linking requirements to your Cameo model, that we've done for years. The others we've also done, but not everybody does it, but you can. You can link, so that the optimal way of doing it is say, okay, I have a particular geometric envelope for this component with certain power constraints. That small amount of information is linked to some component in your 3D model, and there's some actuals that come back, and there's a constraint within the system model that says, is this less than this? And as long as it's, constraint, it's within its tolerances, everybody's happy. As soon as it gets out of those tolerances, some requirement goes red in a table. And at that point, you do something. And yes, there are tools that actually do that. Cyndia from it's a Georgia Tech spinoff from Intercaps, Phoenix Integration Model Center. We've used that to do that same kind of interaction. IBM's Rational Jazz environment allows you to do linked data across like from test cases to, it has that same kind of capability of linked data using something called OSLC links. But yeah, it doesn't, it's, each one of those capabilities is a little bit of work and a little bit of money and a little bit of setup. Anybody else?
For anyone who might want to take the course in the winter, are there any prerequisites, any background they should have before they could register?
Julie, can Did you want to answer that one?
So I guess I could say, like, officially, there are a couple prerequisites listed.
Oh, okay.
So like, there's statistics, and there's like, I think either one of our two foundational courses. I'm sort of like throwing it to you in case someone hadn't taken those
Okay.
courses, if they have a different kind of background, if they like.
Some overall engineering or requirements background, systems engineering overview. I will probably give a little bit of an overview in each of those areas, but if you had some background in the overall systems engineering process, that would be very useful.
What is it again? SYSE 640?
640.
Okay.
Well, thank you for attending, and see you online.
Thank you very much.
Your last name? Sure. Did you ever go to Springfield High